All right. So we're in 15.7. We're one section away of finishing with this entire book. In one day, you'll be able to look at this book and say, I know all of this.
I think I'm supposed to know all of
Or
this.
what was it that we decided last semester? I have been presented the material in this book. Right, Andrew? All right. We are going to talk about the divergence theorem. The nice thing about the divergence theorem is we've done a lot of work to develop all of our tools. So stating it is pretty easy, and working with it, we have all the tools to work with the divergence theorem. So we really don't have to learn anything new to work with the divergence theorem. It just gives us a new relationship. So I want to recap a few things before we state the divergence theorem. So our first big theorem of the chapter was Green's theorem. And Green's theorem, we said in the plane, if we had F, our vector field is mi plus nj. The line integral around our closed path of f dot dr was the double integral over our region of dn dx minus dm dy over our region, so dA. So this was Green's theorem. And if we had a conservative field, Green's theorem says we know that the line integral around a closed path is 0. So we got several different things from using Green's theorem. We also came up with a way of finding area using Green's theorem. If we could arrange it so that dn dx minus dm dy was some constant, then we would just have a constant times the area, constant times dA, and our integral would just be some multiple of the area of our region. So we could use Green's theorem to find area. Then at the end of that section, we derived a vector version of Green's theorem. We said that the integral around our closed path of f dot dr was the double integral over a region of del cross f dot k dA. And here we represented f as mi plus nj plus 0k. So we could do a cross product. And this told us that the integral of the tangential component of f around the boundary of our region was equal to the integral of the curl of the normal component of the curl over our region. So the tangential component around the boundary equals the curl, the normal component of the curl over the region. So this was one vector version that we derived of Green's theorem. We're going to talk about this version in 3 dimensions tomorrow. What we're interested in today was we talked about we derived a version of Green's theorem for the normal component of f. So we said that the integral around our closed curve of f dot n, the normal component of our field, was equal to the double integral over our region of the divergence of f over the region. And this tells us that the outward component of f around the boundary is equal to the integral of that divergence over the region. We're going to work with a 3-dimensional version of this today. This is the divergence theorem in the plane. So we derived this in the plane. We're just going to extend this into 3 dimensions. And that gives us the divergence theorem. So let's state the divergence theorem. So we're extending this idea into 3 dimensions. We're integrating the normal component of f over some closed region and equating it to something to do with the divergence. So the divergence theorem says that the double integral, the surface integral of f dot n ds, which we worked with, we talked about on Friday. So this is our flux integral, equals the triple integral, and we'll call this region D, of the divergence of f. And D is a solid region bounded by a closed surface. And n is the outward unit normal vector. So the divergence theorem holds for a closed surface. We have to have a closed surface. So on some of our flux integrals that we talked about on Friday, we were just talking about the flux through a surface. We could have a plane. We could have the top part of a paraboloid. And we were talking about the outward flux or the upward flux through that surface. For the divergence theorem, we have to have a closed surface. And the closed surface bounds some solid region. So if we were talking, for example, about a paraboloid, we'd have the top of the paraboloid and the bottom. That would be the closed surface. So what the divergence theorem tells us is that the sum of the normal component of our vector field over the surface is equal to the sum of the flux over the sum of the divergence over the solid. So the divergence is telling us something about the flux of our field. And we'll do an example with the divergence theorem here in just a second. So if we have a closed surface and we want to evaluate this surface integral, we can evaluate this triple integral over the solid, and it will tell us the value of this flux integral, this surface integral. Questions about what the divergence theorem is telling us? I'll talk a little bit more about the physical interpretation of the flux and the divergence after we do an example. So just an interesting side note about the divergence theorem, it's also called, you might also hear it called Ostrogodsky's theorem. And Ostrogodsky was a Russian mathematician. He published this theorem first. He published it before anyone else. He was denied a degree in Russia because he was an atheist. So he never gained any notoriety. It was also called Gauss's theorem because Gauss proved it first, but he didn't publish it until later. So it's called divergence theorem. You also often hear it called Gauss's theorem. Very rarely you hear it called Ostrogodsky's theorem, but they kind of developed at the same time. The proof of the divergence theorem isn't really complicated, but it's long and it has a lot of details. So we're not going to go through the proof, but it's not a complicated proof. All right, so let's look at an example of how we use the divergence theorem. Since we already know how to do surface integrals, and we know how to do triple integrals, we have all the tools to use the divergence theorem. So we want to evaluate f dot n ds. The other way that you might hear this stated, or you might see this question stated, is the outward flux of f through the surface so the surface integral of f dot n ds is also, we could also call that the outward flux through the closed surface. This tells us that we're talking about a closed surface. You might also see, sometimes you'll see when you're talking about a closed surface, like I mentioned, this circle through your double integrals. That tells us we're talking about a closed surface. So in this case, our field, our vector field, f is xyi plus yzj plus minus yzk. And our surface is given by z equals square root of a squared minus x squared minus y squared, and z equals 0. So what's the surface that we're talking about here? Sphere radius a, and the z equals 0. What is that telling us? Above the xy plane. So we're talking about a hemisphere. So we have a hemisphere radius a, and we're talking about the upper portion. So we're going to use the, now we know how to evaluate this surface integral. In order to evaluate it for the closed surface, we would have to evaluate the surface integral over the top portion of the sphere, of the hemisphere, and we would also have to evaluate the surface integral for the bottom portion. So we would have two surface integrals that we would need to consider. Well, the divergence theorem, since we have this closed surface, we can just evaluate the triple integral of the divergence. So we're going to calculate the divergence. Del dot f is just y plus z minus y, so that we just have z. And our solid is bounded by s. So we're talking about the upper hemisphere, our radius is a. So what kind of coordinates do we want to use for our triple integral? Spherical, where we have this region like so. This is a quarter of the region. So we're in the first octant, it looks like this. Our surface is z squared, x squared plus y squared plus z squared equals a squared. So we have a sphere. So we're gonna want to use spherical coordinates. In spherical coordinates, so we're integrating del dot f over our solid region, z in spherical coordinates, rho cosine phi. Yes.
Y is it equal to z?
Y minus y is.
Oh, okay.
So yeah, we just took the divergence of this, and I just had a y and a minus. So I just wrote each of the terms here.
Okay.
df, the x derivative with respect to x, derivative with respect to y. So I just wrote each term, and that simplified to z. So in spherical coordinates, z equals rho cosine phi. So in spherical coordinates, we're just integrating the divergence, which is rho cosine phi, over our solid. So we're going to integrate from theta equals 0 to 2 pi. We're going to integrate from phi equals 0 because we only have the upper half here, 0 to pi halves. Rho equals 0 to a. And we have rho cosine phi times rho squared, our dv in spherical coordinates. Rho squared sine phi d rho d phi d theta.
Is that just because you know that z equals rho cosine phi? So
Yep.
you just plug that in?
I just plug that in, so my divergence is just z.
Oh.
And the divergence theorem tells us that this surface integral is equal to the divergence over the solid region. So I just plugged in z here, and then this whole thing is my dv in spherical coordinates. This is not a difficult integral to evaluate. The rho integral, we just have rho cubed, and the phi integral, we have sine phi cosine phi, so that's an easy one to do with u sub. And we end up with, if we go through the evaluation, we get pi a to the 4th over 4. And if you've worked on those surface integrals, this is quite a bit easier than calculating all the pieces that you need to evaluate the surface integral. To evaluate our surface integral, we would have to calculate our normal component, or our normal vector, based on our surface, and we would take f dot n for our normal component. Our normal component is given by del g, or capital G, where G is our representation of our surface, and we would have to integrate that over our region in the xy plane. And we would have two surface integrals, one for the upper part and one for the base, and we would have to add those together. So divergence theorem can save us a lot of effort, a lot of work when we're finding the surface integral over a closed surface. Questions on divergence theorem? All right. I want to talk a little bit about physical interpretation of the divergence now that we've talked about the divergence theorem. So the divergence theorem tells us, I'm just going to rewrite it, that the double integral, our surface integral, our flux integral over our closed surface of f dot n ds is a triple integral over our solid region of del dot f dv. That's what the divergence theorem tells us. The flux through the surface, this tells us that the flux through the surface is equal to the divergence over the volume. So let's consider a really, really tiny surface, ds. So a tiny, tiny, tiny little surface. So we're going to say that ds is small enough that our integrands, that we can consider our integrands to be the same. So the flux, if we have a tiny surface, this is the flux. The flux is approximately equal to del dot f dv. If we have a really, really tiny surface, our flux is approximately equal to this quantity. Or the divergence, del dot f, equals, and I'm going to say, rather than dv, I'm going to say delta v, since we're talking about small things, but we're not necessarily talking about infinitesimal things. So the flux or the divergence is approximately the flux over delta V. If we let delta V become very small, so we're talking about a super tiny volume. So we're going to say that the delta V approaches 0. In the limit, our divergence, del dot F, equals the flux per unit volume at some specific point. So at that tiny point where we're talking about the tiny surface, the flux per unit volume at a point. So this is our physical interpretation of the divergence. The divergence, we can think of the divergence as the flux per unit volume at a point. So the divergence of our vector field tells us the flux per unit volume at a particular point. So it has something to do with the field flowing inward, flowing outward. So if we think of F as a velocity field, the flux per unit volume would tell us how that, if we're the velocity field of a fluid, how the fluid is flowing out at that particular point, how it's flowing in, what it's doing at that particular point. And just as a kind of a hand-waving argument about the divergence theorem, if you think of the flux at any point inside our surface, inside our volume, if you talk about a little volume, if the volume is small enough, you can consider the field constant over that volume. So over that volume, the flux in, since the field is constant, the flux in is going to be the same as the flux out. And you sum that flux over the entire surface, the in and the out cancel each other until you get to the surface of your region. And then, because your volume is super tiny and you're at the boundary of the solid, you're only getting the flux out. So that you're not getting any cancellation there. So that's kind of a hand-waving argument as to why the divergence theorem works. Is inside our region, the flux into a tiny volume is going to be the same as the flux out until you get to the surface, and then you start getting the flux out of the surface. Just a couple more quick things. If our divergence, just some classifications of vector fields. If the divergence is greater than 0 at a point, we call F a source. That should be 0. Greater than 0. F is a source. So the field is flowing out is the way we think of it there. If del dot F is less than 0, we call F a sink. So things are flowing in at that point. And if del dot F, if the divergence equals 0, F is called incompressible. So if we're thinking of fluid moving in and out of a region, if the divergence is positive, we're thinking of fluid coming out. If the divergence is negative, we're thinking of fluid going into the surface. And if the divergence is 0, it's static. Nothing's happening. It's not going in or out. So you might see these terms when you talk about vector calculus. When you talk about the divergence, you might hear F, your vector field, referred to as a source, a sink, or incompressible. So you'll know what that means. Any questions? Yes.
Does the flux or the divergence only ever have to do with liquid?
No, you talk about the flux of an electric field, of a magnetic field. fluid is just, it's a nice way to visualize it because we can think of it flowing, and flux kind of tells us something about flowing. But any kind of vector field has, we can talk about flux and divergence. It's just liquids are a convenient way to think about it. All right, homework. There you go.